everyone. Please, you are all welcome to the 31st Meteorological Virtual Seminar Series, organized by Ghana Meteorological Agency, K University and Global Challenges Research Fund, African Swift. I'm Joyce Amma Johnson, your moderator for today's seminar. The topic we are looking at today is performance evaluation of a high-resolution regional model over West Africa for operational use, a case study of August 2017. Floods resulting from heavy rainfall over West Africa has increased in recent years with serious socio-economic consequences. Therefore, the need to utilize numerical weather prediction models to forecast heavy rainfall events is also rising at many operational meteorological centers in West Africa. This paper evaluates the performance of the Consortium for small-scale modeling model over the German Meteorological Services. In predicting rainfall over West Africa for high-impact rainfall events that occurred between 19 and 26 August 2017, COSMO displays a decreasing scale in producing spatial rainfall distribution as rainfall amounts increase. COSMO is able to reproduce the atmospheric dynamics, modulating the daily rainfall variability, in addition to capturing the daily propagation of the Africa easterly wave trough and the core of the Africa easterly jet. Finally, the incorporation of the fraction scale score metric based on the neighborhood approach could also assist operational forecasters to decide at which scale a severe alert can be issued. So that's the summary I just read. And today we are privileged to have Dr. Eniola from Nigeria Meteorological Agency. He's the current acting dean, School of Postgraduate Studies at the African Aviation and Aerospace University, Abuja, and head of the meteorological department in the same university. So, Doc, please kindly share your screen and let's proceed. Thank you.
So, hello everyone. Can you hear me?
Yes, please.
I'm sorry for this. I have some technical issues here, so I'm trying to sort it out. My camera is not really coming up. So, am I free to now share my screen?
Please, you can share.
So, if you can all hear me, I want to thank the organizer of this seminar. I will be checking out or retiring from operational metrology. I have this privilege to be part of this great revolution in science of metrology. My name is Eniola. The performance evaluation of a high resolution regional model over West Africa for operational use with a case study of 2017 August has been one of our published papers during our projects with the African Suite, which we took part with Ghana Meteorological Agency. And I am not the only one on this work. I have several other scientists who are valuable to the end product of this work. Someone like Kaluka Faro, who is now in UK Met Office, Julian Swidek, who is in University of Leeds, and people from Ahmad, Lawal, and others from the Federal University of Technology, Akure. So, not to waste time, really. Why are we here? My colleagues, what you are looking at presently, they are series of mesoscale systems moving across West African region between 19th to 26th of August, 2000 days of movement. Some places recorded rainfall of more than 150 millimeters in measurement. So along this trajectory of high precipitation, it resulted in massive flooding. The consequences of this are massive, and not because one of the consequences is that it resulted in Hurricane Irma, which is the 5th most devastating. Were displaced, and 4 homes were destroyed. And in Guinea, not only that, it affected more than 3,500 people. About 10 people lost their lives. Generally, in meteorological, across meteorological agencies in West Africa, we all depend on the use of numerical weather prediction system in order for us to make forecasts at any point in time. But one way or the other, we are not really as robust as the international world, the developed world that use what we call convective permitting and sample prediction system to drive their forecasting specifically for high impact weather, which has greatly helped them in accurately getting rainfall forecasts. Unfortunately, even at that, most of us lack the resources to do this in West Africa. So what we do is to resort to the internet. Sometimes some of us access our data by using what we call Windy. Some of us use some of us go to the NOAA website and start retrieving maps. Some of us also go to what every one of us use, which is Puma, and we classify ourselves as we are using meteorological data, but these are maps, and so on and so on and so on like that. We can also go to Met UK. Some of us also use this tropical tidbit, and lastly, some of us goes to this earthnoschool.net. However, despite these shortcomings, some organizations like Nigeria, Senegal, Ghana, still manage to run a limited area model for their daily rainfall forecast for decision making. But these weather forecasts are deterministic in nature. So we decided that to move forward, we have to test or investigate the dynamical drivers, most dynamical drivers that is being used in operational setting, their specific individual contribution and interactive contribution, which is collective contribution in how they modulate heavy rainfall across Africa. And secondly, we want to see the performance of the COSMO model in predicting areas of heavy rainfall and the associated atmospheric dynamics. So this leads us to 3 important questions. Number 1, can a better understanding of the teleconnections between the synoptic processes and areas of heavy rainfall contributes to a better understanding of COSMO model forecast interpretation. Number two, can the use of areas of heavy rainfall is the mean sea level pressure. The second is the cape. The third is the upper air wind. And generally rainfall itself. We simulate all these variables from the COSMO model. How do we use this data really for our work? First, we determine the 24-hour daily rainfall accumulation. Secondly, we determine what we call Cape tendency instead of using Cape actual. And thirdly, we use pressure tendency instead of using pressure action. Then we determine also area of Africa easterly jet and where will the area of Africa achieve computing this. The computation for daily rainfall accumulation is achieved by accumulating the 0600 of today to the 0600 of tomorrow, which is the next day, for us to determine the daily accumulation rainfall of today. The Cape tendency that we use follow the same trend, but a little bit different, because we have to consider the Cape value, the maximum Cape value of a previous day, minus the Cape value of the next day, to determine the previous day and minus the Cape value of today to determine whether the Cape is rising or the Cape is falling. And also the same thing is applied to the mean sea level pressure to determine whether the pressure is rising or the pressure is falling in any areas. Now, the AEJ, we use the zonal wind to determine the AEJ core and the AEJ pool. And we use this value over 700, 600, and 650 hectopascal level. How do we determine these jets? We do not use the conventional way of assuming that the jets must be where the wind is about 25 knots. No. For each level, we extracted the maximum U wind over such areas, plus 5 knots, in order for us to have the axis of the AEJ. Concerning the Africa easterly wave, we use the Africa easterly wave trough. That is following our operational practice. We determine this using the meridional wind that is equal to 0, as 0 tends to minus, not as 0 tends to positive. After that, we subjectively determine the upper part, the upper latitude and the lower latitude, and the upper determine where the real trough will be. This is how it is done for the Africa easterly wave and Africa easterly jet. First, if we have a wind pattern like this, how do we determine where the V equal to 0 is. Because V equal to 0 will be in two places, where you have your trough and where you have your ridge. If we analyze and place over this and isolate where our V is equal to -5 to +5 in green and in red, we'll see that the red is -5. So our 0 would be along here, as our 0 tends to minus about 5, in order for us to have the pool of the jets and the core of the jet, irrespective of the value. Next, we test the skill of the model itself by using simple statistic metrics like the linear correlation. We also use the phase composite, which it is the eyeball, and we use the bias, the mean bias, because we really want to test the skill of the model, not only grid by grid, but to see the performance as we extend the sizes of the grid. What this one does is that it literally converts the deterministic model outputs into probabilistic model outputs. And we use this for rainfall that is equal to or exceeds 90th percentile within this neighborhood size of 30 kilometer to 610 kilometer. For ease of reference and comparison, we regraded the COSMO model into the era interim, and we also regraded COSMO grid into the GPM image at 10 kilometer resolution. Having said that, it's good that we see as results. But first, I will not talk on all the dates. I will just choose some dates here and talk about first the synoptic features of the observed rainfall pattern vis-a-vis their interaction. This is the rain of 24th of August 2017 at the upper left here. And we could see that there are a lot of places that have rainfall that is greater than 30 millimeters and above. There's one in northwest of Nigeria, there's one in Mali, and another one in Guinea. If we look at the Cape tendency, we will see that if we combine these areas, these are the areas where the Cape is increasing, the energy is increasing, there's much instability there. And above it, we have the least decreasing pressure tendency. If we look at it, this rain, especially the one in Nigeria and the one in Mali, are ahead of the Africa easterly wave that we determined. And it's below the Africa easterly jets. But as they move to the west, although the consistency of the Africa easterly jets vis-a-vis where the areas of the heavy rainfall is synonymous with the heavy rainfall here. On the 25th of August, we could see the same thing. We could see that where we have heavy rainfall, there is this combination of in line with these three AEJ core. Because when we look carefully at the distribution of these heavy rainfalls, they are in three places, 1, 2, 3, as replicated in the cores of this AEJ. So AEJ is a very good parameter for determining areas of heavy rainfall, if you ask me. And as it moves again, we can see that all the forcing functions are moving with it. And areas where you do not have precipitation, you could see that it is the area that reflects increasing, decreasing cape and longitude, please. And we could see that on this 24th, the only attributed factor for rainfall west of the meridian is just the Africa easterly wave. You can also see on the 22nd that the arrangements, these synoptic features are really not organized west of the prime meridian, but the effect of the Africa easterly wave trough that is in blue is effective. How do we run this COSMO model for this experiment? Just let me say a little bit about the model setup. Well, COSMO model is a limited area model from DWD, as you all have known and have worked with. It is initialized with ICON global data, but for this experiment, we use the COSMO for a resolution of 7 kilometers. It starts longitudinally from 14 degrees east and about 529 grid along the longitude. It starts the latitude. That is why for about 60-hour simulation, it took us 20 hours to run this, and at 3-hour time step. So it is very, very tedious and rigorous. We could simulate about 56 variables in the model level at the single level, and we simulated about 8 variables at the upper level, and where we took those Cape mean sea level pressure that we use for this study. So the first thing that a forecaster wants to see is how the model is compared to the observed visually, because that is where they get us. The forecasters will always look for this in order for them to say, your model is not working, your model is not working, get away. So let's see how eyeball to eyeball, how the COSMO model perform against the observation that we use, the error entering and the GPMI in terms of the rainfall. Now, on the 21st of August that we have seen, the areas of increasing cape could also be seen here in Nigeria, somewhere here in Mali, but it is not really represented in, let's say, Syria alone. Most of Nigeria has the areas of decreasing cape on this day. So a forecaster will not see this and say, oh, your model performed very well. But the same thing is not said for the 22nd, when the system had already moved. When the system moved, we could see that most parts here in the COSMO model has the same decreasing cape as it is represented in the observed. But when we come to where it is very, very necessary, then the Cape value of the COSMO model failed here. Instead of increasing Cape, it's giving areas of reducing Cape. If we look at 25th and 26th of August, the scenario is a little bit different. It performs better here than what we saw on the 21st and on the 22nd of August. We could see vividly that the performance, except over this area, the performance actually improved a little bit, especially over areas like Mali, Burkina Faso, and Nigeria, southern Ghana, I think, and Togo. So let us look at the mean sea level pressure as simulated by the model and as observed. We could see some kind of improvement in the way COSMO simulated the Cape tendency, the pressure tendency here. The areas of the falling pressure is the same thing, almost, with the areas of falling pressure as observed. And the same thing occurred when the system moved. On the 25th and on 26th, the broad elaborated areas of the falling pressure in as observed is really represented here using COSMO model. Let us look at how it predicts. Hello, can you hear me? Can anyone say hi?
Hi, somebody's online.
It's really the noise on the, at the background is distracting. Okay, now let's continue with how the model represents the areas of Africa easterly jets. Yeah, if we look at the red here is as simulated by COSMO model, and the black line is as observed. When we look at carefully, we could see that, yeah, this is a good impression from a 7-kilometer resolution model, a deterministic model, but it lags by about some kilometers behind the observed, irrespective of the day that we consider. So again, if we look at the observed Africa easterly wave throughout, marked in dashed blue lines, and we superimpose the one that is simulated by COSMO model, and we'll give it a green line. So remember that the areas of our Africa easterly wave is where the V equals 0 tends to minus. So it means that instead of the COSMO model wave is always also ahead of the observed wave. There's also a spatial deviation here. So how does the producibility or the reproducibility of this COSMO model in producing this synoptic affects its rainfall forecast? Of course, it is clear. Here is the observed satellite data rainfall GPMI March, and this is the rainfall from COSMO model simulated. On the 24th of August, the simulated rainfall expected that the areas of every rainfall would be here, for instance, and it is shifted to the north as observed. So it lags again by about some kilometers to backwards. Not really too good in Gambia, for instance. And during this day, except for the coastal areas of Liberia and Sierra Leone. It means that how COSMO was able to reproduce the driving forces does not really translate into it producing rainfall accumulation. How do we correct this? Now, we really need to test its scale first, 26th of August. And if we consider the pressure, you could see that almost explicitly, COSMO is able to predict it. However, we cannot say the same thing for the Cape, because for the entire region, COSMO really overestimates the Cape Valley. It's also reflected in the rainfall value as a result, because to the east of the prime meridian, there's a whole lot of dryness, a whole lot of wetness, and to the west, there is a whole lot of dryness as forecast by the model. If we look at the correlation between the model and the observed, we can see that the correlation of the Cape here and the rainfall, well, it is complicated, but we could see that despite this complication of these biases all around, many areas still have correlation of more than 5. And we could see that it's explicitly correlated with the mean sea level pressure. We are getting somewhere. The next is what we call fraction forecast verification. And fraction forecast, as I have said, is to correct all the inherent biases due to lagging, due to underestimation, and lagging that we call double penalty in theory. The work of the fraction forecast really is to turn this deterministic forecast into a probabilistic forecast, so that at a specific neighborhood, we could determine at what neighborhood will our forecast be correct for probabilistically. Because as you can see now, these moving objects are the fraction forecast over the observation in blue. You can see that it has a little bit corrected the lagging of the rainfall. Incredibly, at least, even if it is about 0.1 or 1%, forecasters can still have something to say to correct these biases. And not only over here, we can also see how it corrected it over Senegal, how it corrected the underestimation. Why the fraction scale score becomes necessary. So we use fraction scale score to determine when, at what neighborhood, should we apply the fraction for the fraction forecast will be good. It means that for this particular case study, over this West African region, at 300 or thereabouts, we could apply this fraction forecast. In summary, if we take the rainfall and synoptic teleconnection, we will see that all rainfall dynamics move in concerts, but ahead of the Africa Easterly Trough. We know that. Secondly, we have seen that the position of other drivers considered ahead of the Africa Easterly Wave Trough are sequential in order of pressure, K, AEJ, particularly east of the prime meridian. We have also seen that these areas of heavy rainfall often coincide with where AEJ occur. It can be the entrance or the exit or directly in there, but ahead of the Africa Easterly Wave Trough that precedes it. We have also seen that while areas of heavy rainfall east of the prime meridian are mostly associated with combined interactions of all these forcing functions, the Africa Easterly Wave Trough seems to appear to be a distinct atmospheric dynamics that is associated with heavy rainfall west of the prime meridian. This is what we saw in Senegal, Gambia, what have you. So let us look at how the COSMO model performed in summary. We have seen that COSMO model exhibits some distinct characteristics in West Africa in simulating and modulating drivers and heavy rainfall. We have seen that COSMO model is able to predict their daily evolution and yes, sometimes the intensity of the AEJ and Africa Easterly Wave with some lagging some kilometers behind the actual. Well, we will say that the model correlation in predicting Cape, the Cape tendency is a little bit good. It was somewhat good over Nigeria and some places like in Ghana and Sierra Leone. It could explicitly predict the spatial temporal evolution of the main sea level pressure and the main sea level and the pressure tendency with a correlation of about 0.85 in most places. We have seen that the COSMO model reduces in scale as rainfall value tends to 30 mm. But despite this spatial temporal biases, the model have correlation that is greater than 0.5 in most places, considering the rainfall. If we apply the neighborhood technique, we have seen that the neighborhood sizes increases there in a significant improvement in both the forecast fraction and the forecast score as the neighborhood sizes increases. So what have we seen? What can we take on? The scale of the model in predicting atmospheric dynamics does not transform into its predictive scale of producing rainfall. Then, two things forecasters can do in operation. One, forecasters could leverage to estimate the likely areas of heavy rainfall by determining the position of Africa Easterly jet core from the knowledge of the position of areas of the least falling pressure in the model, in the COSMO model at this time. Secondly, forecasters can utilize this neighborhood forecast fraction method to have a little bit idea of how to correct the double penalty, which is a spatial displacement error that is embedded in the model. I would say that you can access this work. It has been published in the Royal Meteorological Society Journal, and that is the link to get there. I am going to stop here. I'm going to say a very big thank you for giving me this rare privilege and to share this work with.
Thank you. Thank you very much, Mr. Onyola. Please, I want to ask if there's any question from the audience. You can feel free to post, or you can unmute yourself to ask your questions.
I don't even see myself. This is me. This is me before. I can't see.
Hello, Lisa, I have a question.
Please go ahead.
So I just learned from the Ghana Meteorological Agency and with the research department to know some few things. You mentioned of numerical weather predictions, and you made mention of an FSS and a COSMO. I just wanted to ask, you see, for numerical weather prediction models, I'm still do whatever output you want. And for nowcasting, it has a period of, let's say, 2 to 5 hours for nowcasting. So I was thinking you were trying to be like the numerical weather prediction is better. But there are some bases in meteorology that every meteorologist knows that the atmosphere is very chaotic, and let's say systems can develop at any time. So maybe we can model something with the numerical weather prediction models, and also we can have an output from the, let's say, nowcasting. But with the numerical weather prediction model, maybe we can do it for some time, like a period of time. But the nowcasting is helping us know, let's say, in the next 2 hours, in the next 3 hours, in the next 4 hours, what is going to happen. So should we downplay the outputs of the nowcasting and solely depend on the numerical weather prediction models?
Yeah, that's a very brilliant question. Very, very brilliant. And you know that the atmosphere, that is why we have a scale of atmosphere that is at every scale. Atmosphere is important because the short term is what led to the long term. In forecasting, you know, they are in layers. As we have very short time, where the seasonal to seasonal forecast range, we have the seasonal range, and we have the climate range. All this compensates for one another. The idea for a forecaster is to look ahead first. What is going to happen 24 hours ahead? It is just to test our human capacity in developing all these skills. Now, if he now saw a change if you now sees any change in the nowcasting, like in satellites, real-time satellite, what do you call it, images, then he could quickly correct what he has already predicted for 24 hours or for 24 hours precisely. So it is a very useful tool to use, nowcasting tool. That is why during the African Swift thing, all of us were sponsored, funded to have a nowcasting facilities in all the operational centers, and it's helped a great deal. So that's a very fantastic question. Thank you.
Thank you very much. And there's a follow-up one. So you made mention of the FSS and you made mention of the COSMO. So I wanted to know that this, let's say, fractional scales, is it incorporated in a numerical weather prediction model, or you actually model those things on their own? And when the modeling is done, that is when you use the FSS to do the fractional correction.
Another brilliant. Please, what is your name?
Ajaku Daniel.
Actually, now this is the beauty. The first time we saw the fraction forecast was in Kenya. We are all there, and that I had this question that you just asked before I was able to now incorporate this. That what is this? They say it's called fraction forecast. It's in Met UK office. So what we did is to take the COSMO output, okay, the COSMO output for rain, for each rain day, then compute the binary of each day by changing the dimension, by changing the spatial resolution. For instance, at a specific spatial resolution, let's take 10 kilometers, what is the probability of this occurring? Then we change again at 30 kilometer resolution. What is the probability of this again? It's an algorithm written that is used with the numerical weather prediction outputs to generate this fraction forecast. And it is generated for each of these neighborhood size. We call it neighborhood size. It is, I actually call it resolution, because we apply this binary from a higher resolution to a very low resolution, so that we can have a probabilistic distribution of it. We won't be talking about a deterministic one-time result. So we will talk about multi-layer multi-layered resolution result. That is the beauty of it, and that is how I have been able to use it. And it is operational. We can make it operational because the model works seamlessly.
All right, I'm very clear with it. Thank you very much.
So I can stop sharing. Is anybody there?
Yes, please, we can hear you.
Okay.
Hello.
So any question again? Who is our coordinator?
Yes, there's a question on the Okay, Doc, so thank you for the presentation. And you spoke about pressure and cape, wind tendency, and later showed a wind chart. I wanted to ask if the wind action is important to mesoscale system propagation or implicit. So if it does, should we consider the wind tendency of the specific time frame for the forecast?
Yes, it's also a very good. When I was a bench forecaster, there are lots of Poisson functions that we use. We use vorticity, we use divergence, and other instability indexes to determine how unstable the atmosphere is. But my experience has shown that we only named few of these: the baroclinicity and the barotropicity, and which is the cape tendency and the pressure tendency. Now, we can determine this at every hour. We can output this cape and pressure tendency every time that we want it. But because we wanted to see daily rainfall, we did what we call P24 in our alpha X-ray the messages. You know, there's a section for P24 for P24. Instead of me having P24 alone, I added C24, C24, C24. So that is why I centered on the daily cape tendency and daily pressure tendency. And for me to have that daily cape tendency, I use the maximum cape for the day between the 06 hour of today and the 06 hour of tomorrow. And the same thing I did for pressure. Instead of me to use pressure at 06 hour of today, I use the 00 mean sea level pressure and minus 00 mean sea level pressure of today from that of tomorrow to get what the pressure tendency of tomorrow would be. I hope I managed to answer a little bit.
Please, is there any other question? Okay, so in the absence of further questions, I would like to thank you, Brooke, for the presentation. It was great. And to our participants, we also want to say a very thank you for joining. And we hope to see you during our next seminar. So please kindly be registering the Google form so that you'll be able to get notifications concerning the seminar we organize. So the seminar the recording will be shared to those who registered, to your mails, so that you'll be able to have access to it. Thank you very much.
All right, thank you, everyone. Good to be here. And thanks for
you.
listening to me. Bye.
Bye.
Okay. Bye-bye. Yeah, you're going to have the copy of the presentation.
Yes, I will send it
Someone
in
is asking.
PDF form.
Yes, please.
All right.
Thank you.
Now,
And